invariant measures for multiline asymmetric exclusion processes. So Christophe, the floor is yours. You can start when you want.
Okay, can you see me, by the way, or I can't see myself?
No, we cannot see you.
Ah, so is it a problem, or maybe it's
not, so if it's too complicated, no, it's not a problem.
Oh, I have to.
Mainly
just okay. Now you can see me.
Ah, yes. Yes. Yeah.
Okay. Thank you very much for the invitation. As you can see from the title, this is joint work with Guidi Amir, author Busani and Saada, and we investigate the problem of invariant measures for a certain class of exclusion processes. So I assume that a number of people in the audience are acquainted with exclusion processes, but if some are not familiar, do not hesitate to stop me. So the plan of the talk will be in the first part I will talk about the background. So what is known and for the kind of things that we investigate, and then I will state the model we investigate, which is something in between dimension 1 and dimension 2, and also what is left open and that we would like to solve. And then depending on remaining time, I will say a few words about the main ideas of proofs. Okay, so first about so this is a series of important references. Of course, I'm not claiming to be exhaustive, but let's say that these are references which are closely related to our problem. And I would say that okay, so the reference number 2 is the mother of everything. I will not present it. And the other references, I could say that in some sense, the problem we study is in the wake of these references. And the references, reference number 7 is a recent preprint which is investigating a similar model to ours, but in the symmetric regime, and we are more focusing on the asymmetric regime. So the two things are kind of complementary. So the exclusion process, just a few words to remind what it is, if necessary at all. You have a physical space S, and you have these dots which we call sites, and on each site there can be a 0 or 1 particle, and a particle can jump to a site which is empty. This is the exclusion rule. And for each bond, you have a jump rate, which is in fact a jump kernel. P of xy is the rate at which a particle at x is attempting to jump at y. And there are several ways of constructing this, either from Poisson processes or from a generator. So here is the usual formal definition of this process through a generator. So you can see that the state space of this process is here. Eta is the microscopic state variable. Eta of x is the number of particles at site S. Here it can be 0 or 1. We are mostly interested in the case where S is countably infinite, because this is the interesting case. Otherwise, it's a Markov chain on a finite space. And this is the generator which tells the same thing as on the previous drawing. And one of the basic questions that one asks, as one would ask about almost any Markov process, is what are the invariant measures? So try to describe all invariant measures. So via Choquet-Denis theorem, to describe all invariant measures, in fact, means to describe all extremal invariant measures. Okay, and so this is what we are going to study. So there are a number of very classical results, which you can find in Liggett's book. In certain cases, there are well-known simple invariant measures for the exclusion process. These are product measures in the sense that each site is independent from the others, and each site has a Bernoulli distribution. So, for instance, if you make the assumption that the kernel is doubly stochastic, then you can show that there is a homogeneous product invariant measure, product Bernoulli invariant measure. So, for instance, this is the case if you are on ZD and if the kernel is the existence of product measures which are reversible, and you can find such measures if your kernel has itself a positive reversible measure, which is denoted by lambda. And if you have such a lambda, from this lambda, you can construct a density profile. Lambda, in fact, is interpreted as the fugacity. And if you set rho equals lambda over 1 plus lambda, and if you take the product measure, which has a parameter rho of x at each site x, then this will give you a reversible measure for this model. And one remark is that, in fact, this is the classical way this is stated in Liggett's book. You do not really have to take this fugacity as an intermediate object. You can directly write a condition in terms of the density profile to say that there is a reversible measure, and it is this, say, nonlinear detailed balance equation. Okay, so you could, but the classical form which is given in Liggett's book is this one. Okay, so is this clear so far for everyone? So this is a classical history, and then so these are some well-known simple invariant measures, but now the problem is what are all invariant measures, and this is much more difficult, and in this degree of generality this is not solved, except in the case where P of xy is symmetric. And from now on we are going to focus on the case where P is translation invariant at least in one direction and has a drift. And what is important about the drift, we have seen that in this situation we had homogeneous invariant measures. What is important about the drift is that you can have this kind of things, which are well known, I guess, by many of you, which are called blocking measures. So, for instance, if you have the ASEP where each particle can jump just one unit to the right, you can see that such a configuration is frozen, and it is an invariant measure. It's an invariant measure which is more generally carried by a countable space of so-called blocking configuration. And what a blocking configuration is, a configuration which is going to be full rightwards from a certain point, and which is going to be empty leftwards from a different point. And the set of these configurations is countable. You can restrict the model to this. Okay, and in one dimension, when there is a drift, there exist a number of results. This started in 1976 with Liggett, where the main idea is that with various degrees of precision, if you try to know all invariant measures, you have either the homogeneous Bernoullis or measures which will look like this kind of thing. Of course, this is very special because I took a very special jump kernel. So just for a quick overview of known results, we have to give a few definitions. So what is drawn here is called the blocking measure. As I said, a blocking measure is by definition a measure which is supported on this space, the space which is drawn here, and there is also a weaker notion of profile measure, which was introduced in the 2000s by Bramson, Liggett, and Mountford, which says that the mean number of particles goes to 0 at minus infinity and 1 at plus infinity. It's weaker than blocking measure. And when you restrict the process to this blocking state, you have a conserved quantity, which is the number of holes to the right minus the number of particles to the left. So in fact, if you want to have extremal measures, you have to condition upon this conserved quantity. So it happens in some cases that you have explicit blocking measures which are product, but they will not be extremal because you need this conditioning. So the classical result by Liggett is that you have these blocking measures. If you have a nearest neighbor random walk which goes P to the right and Q to the left, then you construct this density profile, which is in fact obtained from the reversibility equations I gave at the beginning. And this, if P is bigger than Q, this is going to extrapolate from 0 to 1. And then you can condition these measures on the conserved quantity, and the classical result by Liggett is that this gives you all invariant measures. You have the homogeneous measures, and you have a family of measures which are in fact shifts of one measure. You take this one, you condition it with respect to the conserved quantity. The constant C doesn't play really a role. If you change it, it will just amount to shifting all the measures. Okay? And the simplest example is if you can just go to the right one unit, then you get as invariant measures the shifts of these configurations. Okay, so in the world of exclusion process, there are various degrees of difficulty. There is totally asymmetric, there is nearest neighbor, and then there is non-nearest neighbor. So there have been significant improvement of these results to cases where the jump kernel was not nearest neighbor. So for instance, Ferrari, Leibovitz, and Speer proved the existence of a blocking measure under an assumption which says that the drift pushes very hard to the right, but you don't need the walk to be nearest neighbor. Bramson and Mountford gave a very general result, just assuming positive drift, but finite range. And then Bramson, Liggett, and Mountford proved the existence of a blocking measure, not necessarily assuming finite range, but you do need a certain set of assumptions, and one of these assumptions is a weakening of this one. And all these results tell about existence of blocking measures which are not at all explicit. So these are abstract results. This is for existence of blocking measures, but what about description? Okay. Description is, you would like to have a theorem like this one. So can you have description in these more complicated cases? So in the paper of Bramson, Liggett, and Mountford, there is also some description. There are results, and the most general result is that you always have something like this, that if you try to describe all invariant measures, it's either the Bernoullis or a set which is the shifts of a unique profile measure. You do not always know whether this measure is a real blocking measure, but it's a profile measure in the sense that I define here, which is a weakening of blocking measures. Okay, so this is an overview of what is known in dimension 1. And so a lot of things are known, but there are one of the main open questions, for instance, is are there cases where there exists a profile measure which would not be a real blocking measure? Okay.
Christophe?
Yes.
Can you hear me? Yeah. So you talked about existence for blocking measure. Is this uniqueness straightforward if you once you fixed this H thing, or is there something to do?
Yes, the uniqueness is proved even at the level of profile measures in the paper of Bramson, Liggett, and Mountford. And since a blocking measure is a fortiori a profile measure, then if you get one, it will be unique up to translations. Does that reply your question? Is that okay? So then one of our motivations was to make a little step towards dimension D, which is much less clear. So as I wrote in the abstract, the main reference which exists in dimension D is a paper by Bramson and Liggett, where they set some foundations and conjectures. But one is still far from having a description like the one I showed before. And their idea was to introduce what they call the V homogeneous and V profile measures. So in dimension 2, a V homogeneous measure is a measure where things would be variable, say in this direction, but which would be translation invariant in all directions or orthogonal to V. Okay, and a V profile measure would be the generalization of a profile measure in the sense that it would be a measure which would tend to 1, at least in mean, at plus infinity along V, and to 0 at minus infinity along V. Okay, and so they gave, for instance, some necessary conditions on V for such measures to exist, and some examples of such measures. So you can construct examples, explicit examples of product V things, and this is the formal definition that they give of V homogeneous and V profile measure. And here is the example that you can construct is a nearest neighbor random walk in dimension 2 with moving right with right P and left with right Q, and similar in the vertical direction. And if you try to construct product measure, you see that you have 3 choices for V. Okay, you have one choice. This looks like the formula I showed before. You have one choice which will give you a measure which will vary both in the X and Y direction, but really the interface would be this vector. Or you can choose your measure to be to depend only on X, in which case it would be a V profile measure with this V. Or you can choose things to be constant in the X direction, in which case it would be a V profile measure with this V. Okay, and but there is no characterization result, and it is not known for which V's there exists such measures. At least you have these examples. Okay, so some open questions that they ask at the end of their paper is, for instance, is every invariant measure V homogeneous for some vector, and is every invariant measure V profile for some vector? And then they say, well, it's difficult problems, and maybe it would already be interesting to try to answer these problems for a simpler toy model, where one of the directions would be finite and cyclic, and they call this the ladder process. So say the y direction is the torus, and so in this context, V homogeneous, they say, would mean rotational invariance. So the problem would be if you have a ladder process that I'm going to define in a moment, is it true that any invariant measure is invariant by rotational shifts in the torus direction? And V profile would mean this, would mean that you look at things in the infinite direction. Okay. So in a certain extent, we tried to address this type of question for a kind of a ladder process, and also to give some description results for this kind of ladder process. So let me define the basic model that we studied. Actually, we can look at more general models. This is a model where the vertical direction has size 2. We can go to bigger sizes, but in fact, in our arguments, there is an abstract part which is fairly robust, and there is a part which is based on analytical computations, which uses the fact that the vertical dimension is 2 to get more precise results. So some general abstract results will be available for an arbitrary vertical size. So our basic model will be nearest neighbor on each lane. You can view this as a 2-lane exclusion process.
I have a question about so you say arbitrary size in this vertical dimension. Can you take like z times an arbitrary graph, for instance, for the general size of the result, or you need a torus of size of some?
No, we don't need the torus. Actually, the torus is what we wrote in the paper, because the torus was related to the question of Bramson and Liggett. So we wrote things a bit more in detail for the torus, but the vertical direction, I think I will say it a bit later. It is possible to have extensions about this under certain assumptions. The basic model is so a 2-lane exclusion model, which also may be seen as a traffic flow model. It has been studied as such in the physics literature. So you have jump rates D and L to the right and left respectively, which can be different on each lane, and then you have vertical jump rates from the top lane to the bottom lane, and then you have a drift on each lane. And we try to study situations where the drifts could possibly in different directions, or one of the drifts could be 0, or both drifts could be 0. But our focus is on the asymmetric case. So the first thing that you can construct as explicit measures for this model is measures which are going to be shift invariant in the infinite direction. And if we compare it to the Bramson-Liggett picture, it would somewhat be related to this case, in fact. And to do this, well, you can construct measures where you have what we call a relaxation relation between the density. You can possibly have 2 different densities on each lane, and you have a relaxation manifold like this one. And then then the vertical direction here can be 0 or 1. And you can construct product measures which will have this profile, this kind of profile. And so for y equals 0, this is going to be row 0. For y equals 1, this is going to be row 1. And this formula gives you pairs of densities which belong to this relaxation manifold. So in a sense, you can view these as a 0, 1 profile measures. In fact, these measures are kinds of mixtures of the two situations I reviewed at the beginning, which was the reversible and the non-reversible. In fact, in the horizontal direction, this is like an asymmetric homogeneous measure, which is not reversible, but in the vertical direction, it would be reversible. And although it is not very visible due to the fact that the vertical size here is 2, you really have to view this structure as the fact that vertically it has the structure of a blocking measure. So this is the first. This is when Q is different from 0, and when Q is equal to 0 is a degenerate case, which has some interest because in some respect it might look simpler because. But in other respects, it causes some degeneracy problems, and it also allows us to get precise results. So for Q equals 0, you don't have this, but the vertical structure will in fact look like where was that? Would look like something like this, except that it would be on a finite size. So the vertical structure would be obtained like this. So if you parameterize the global density between 0 and 2, you will first, so Q is going from top to bottom, so you cannot get up. So the measures you obtain is first by filling the lower lane with a density, with an arbitrary density. And then once the lower lane is full, you can complete it by filling the upper lane with another arbitrary density. Okay. And so in general, these two parameter family of invariant measures, in fact, can be reparametrized by a single parameter, which is natural because in fact there is just one conserved quantity. It is here, and so you can find a parametrization with a single density, which will represent the global density between 0 and 2. So, for instance, in general, this parametrization is not algebraically simple. And if you want more lanes, it is not even explicit, but you can show that it exists. But I mean, I would say the obvious cases is, for instance, if P is equal to Q, and if you want overall density rho, then you will put rho over 2 on each lane. Whereas if Q is equal to 0, we are back to what I wrote before. So here what I denote by rho tilde of rho is the density rho tilde 0 of rho is the density on lane 0 that you get if you want the global density over the two lanes to be rho. Okay. So is that clear so far, or any questions? So now I would.
Yes.
Yes.
Yes. So in order to have a blocking measure on the vertical direction, do you need somehow that there exists? I mean, your graph is finite in the vertical direction. So
yes.
So do you need that the dynamic restricted to the vertical is reversible? Because to have a blocking measure in finite, we need a reversible on this finite graph. So
in this case, where the size is 2, it is automatic.
Yeah,
that is for sure. And
if you have a three-point segment, it seems that it would work, but 3-point circle, it seems much more difficult.
Mm-hmm. Do you need? Yes. Would you need reversibility? So the question is the question you ask is a question for a one-dimensional exclusion process. In fact, no, a one-dimensional process on a strip. Whether it can have blocking measures if there is no reversibility. No? Because I am describing things which are shift invariant in the infinite direction. So
on a finite space, blocking and reversible is not exactly the same thing.
Yeah, no, because precisely if you go back to the results I mentioned, these ones. These people spent a lot of time showing that there could be blocking measures without reversibility. Blocking measures which are by no means explicit and which are not, I think, reversible. They don't say whether they are, but at least these blocking measures are not obtained from explicit reversibility computations, but by abstract arguments. But this is for infinite space, okay? To prepare for some description, I need to try to define analogs of blocking measures in our context, so we can define what is a shock measure. In general, a shock measure is a measure which is going to be asymptotic to a Bernoulli at -infinity and +infinity. We define its shock amplitude, and since you have two lanes, the density can range between 0 and 2. So the notion of a profile measure should be defined as a shock measure, which is either 0,2 or 2,0. In fact, of course, it clearly might depend on the sense of the drift, but you can restrict the parameter range and we will restrict the parameter range by symmetry considerations in order to have just this case. Okay. And a blocking measure will be defined in a similar way as a measure which is supported on this kind of configurations. That is that rightwards from a certain point, then the ladder is going to be full, and leftwards from a certain point, the ladder is going to be empty. So this is stronger than a profile measure. And again, when you restrict the process to such configurations, you have the same kind of conserved quantity, which here I denoted by H2. But there is a difference that if you count if you shift the configuration, okay, in the single lane case, you could see that you had this relation, this shift relation, and if you have two lanes, then if you shift the configuration, then the conserved quantity is modified by 2. This means that you have two families of conditionings, and in general, you do not expect to have a single shift, but you will expect to have two families of shifts, which are singular with respect to one another. So to give a general flavor of our results, so what is complete, what is partial. So there is one case that we did not treat in this paper because it is it belongs to a really different technology. It is actually, we think it is a non-gradient diffusive model, and our paper is based on coupling methods. So it is a different world, but it is the case where P is equal to Q, so it is symmetric in the vertical direction, and the drifts on each lane are opposites to each other. So we can say something about this case, but not as much as about the other cases, because the techniques are not the right, the optimal ones for this case. So the general idea is that the behavior will depend mostly on the drift and on the ratio between P and Q, but not only. And in some cases there can be some microscopic details that matter. So if I exclude this case, which is, I mean, even not excluding it, the general structure theorem is that the invariant measures, you have the new rows. So the new rows here are the measures which are invariant in the infinite direction, but not in the vertical direction. And then you have two families of shock measures. And what we can say about these families depends on which part of the phase diagram we are in. So except in this annoying different case, what we can say is that up to shifts, each of these families is finite, and that generically, except maybe in the degenerate case where Q is equal to 0, this set will contain at most one measure, and this set will contain measures. And the fact that this set contains at most two measures is in fact makes sense, because there are concrete examples. This would correspond to profile or blocking measures. And in certain examples, you can really see that there are exactly two blocking measures up to translations, and not just one blocking measure, for the reason I mentioned here, that there is odd and even conditioning. Okay. So this is the general. And in some cases, there are phenomena which are a bit different from what one might expect in dimension 1. So first of all, I will start with a symmetry reduction. There are symmetries in this model, and you can reduce the set of parameters in such a way as to relations. There are different types of symmetries. There is particle hole symmetries. You can exchange lanes, and with these symmetries you can reduce the parameter set to this one. And for instance, this will allow you not to be bothered with whether the profile measures are 0, 2, or 2, 0. So if I choose this part of the phase diagram, the profile measures will be 0, 2. So the first case, which is maybe not very surprising, which is not our main focus, but it can be treated also by our methods. But I think this case can be treated in a bigger generality by different duality methods in the paper I mentioned at the beginning. This one, which which focused on symmetric situations, but where our approach also gives results here. The point is that I think that in their paper they use duality methods, so they can, for instance, access inclusion type processes which are not attractive, whereas we have to work with attractiveness. So in this case, we find that there are only the measures which are invariant in the infinite directions. There are no blocking type measures. This is not quite a standard result because this is not a symmetric exclusion process, because this case includes the case where P and Q are different. If P and Q were equal, then you would have a real symmetric exclusion process, and this would be a special case of the general theory on the symmetric exclusion process. Okay, then okay, maybe the first case to look at is the one where both drifts are positive and Q is positive. And this one we can, in this case, we can have a reduced set of parameters to describe the behavior of the system. So what we can show is that P2, so the 0-2 shocks, this set is either empty or contains exactly two blocking measures. Okay, we cannot say exactly when there are blocking measures because, as we saw, this is already a non-trivial problem in dimension 1. So we hope, for instance, that maybe using some ideas from Bramson Montford, which used hydrodynamics, which is a part of our project for this model, this could be done, but it is not obvious to say if there are blocking measures in cases where you cannot really exhibit them. Okay. So what we can show is that there is a strange constant, which is probably not optimal, which is probably an artifact, but which has two great qualities for us. The first one is that it's explicit, and the second one is that it's not zero. In an open part of the phase diagram, so in a neighborhood of the place where D is equal to 1. Is it 1 or 1/2? I think it's 1/2. Sorry, there's a typo here. So it's 1/2 means that it's the same drifts on both lanes. So in the neighborhood of where you have the same drifts on both lanes, and R is small enough, which means that there is a strong bias either upwards or downwards, then we get a complete description of the invariant measures, and we can show that there are only the measures which are invariant in the infinite direction, so the, say, 1-0 profile measures. And that in this case, there could be no blocking measures or two blocking measures, but there cannot be shocks of amplitude 1. If we add the assumption that the ratio D0 over L0 equals D1 over L1, then we can construct exactly explicit blocking measures in these cases, and then we get a complete description saying that you have the 1-0 profile measures and these blocking measures. So these blocking measures look a bit like the blocking measures. So if you remember the Bramson Liggett picture, you had these cases with only one direction. So the blocking measure that we find in this case is would look like this one, and so you can construct it explicitly, and it is this one. So in the language of the paper of Bramson and Liggett, we might say that this is a V profile measure with this V. Okay. And so if you condition this product measure on your conserved quantity, being either odd or even, you will get two families of shifts, and this will give you the whole description of the invariant measures. Okay. One case which is a bit special, where this formula doesn't make sense, is when L is equal to 0. That is when you have two ASEPs on each lane. And in this case, you still have these blocking measures, but the blocking measures will look like this. So on each lane, you will have a blocking measure which looks like the blocking measure of ASEP. But then here you could, so you will have these measures with nothing here. So just these measures and their shifts. This is the first family of shifts. And the second family of shifts will be a measure where you add a particle here with this probability, or a particle here with this probability. Okay, this is the analog in the. This is what it means in the totally asymmetric case. Okay, so that was for case one. So with two drifts, two positive drifts. What happens when the two drifts are of different sides? We have a condition which says that if Q gamma 0 plus P gamma 1 is negative, then there can be no profile measure. Okay, so if there is a kind of sufficient competition between the positive and the negative drift, then there is no profile measure. Okay. Then there are cases where we can show a bit more partial results. So, for instance, if the drifts are opposite, so if the drifts are opposite, we already saw that in the case P equals Q, this was the bad case, which we think is non-gradient. In this case, we do not know. We still have this structure of having one shocks and two shocks, but we do not know if there are finitely many one shocks and finitely many two shocks, or if there are any of them. If the two drifts are exactly opposite, but P is different from Q, then what we can show is that the set of one shock could possibly contain two measures, but we do not know if they really exist. Okay. Okay. So I don't know how much time is there left. Can you?
Yeah, you can have 5 minutes.
Okay, so 5 minutes. I have to.
We have time for questions. Yeah.
Okay, so 5 minutes. I will describe the remaining cases. So the main remaining case is what happens when Q is equal to 0, which is the degenerate situation. So in this case, we except when the two drifts are equal, where we have a remaining uncertainty, we have a complete characterization of what happens. the behavior depends on the drifts, but not totally. There is something different that happens if the two TASEPs go to the right and if particles cannot jump left. So first, if this is not the case, so if at least one of the lanes can jump left, then we have a complete description. We have the measures which are shift invariant in the infinite direction. And we do have shocks of amplitude 1. But these shocks are special. They are partial blocking measures, actually. These are measures where one of the lanes is carrying a blocking measure and the other lane is either full or empty. Okay. On the other hand, if the two lanes are totally asymmetric to the right, say, and you cannot jump left with the Q equals 0, we have a complete characterization. We still have these blocking measures, but we have a family of we have the partial blocking measures, but we have a family of blocking measures, but which depends on two independent parameters. That is, you can place a 0-1 shock on each lane almost independently, except with the constraint that the shock you place on the upper lane has to be to the I think right of the shock you place on the lower lane. Okay, so these different cases are summarized on these pictures. Okay, so when Q is equal to 0 and you have two positive drifts, you have these partial blocking measures. So this is each lane. So this picture means that you have a blocking measure, but with PQ, so which is not abrupt. And this picture means that you have a blocking measure, but with a totally asymmetric particle system, so which is abrupt. Okay. So these are the possible partial blocking measures with one lane empty, and these are the possible partial blocking measures with one lane full and the other one carrying a blocking measure. And in the case of two totally asymmetric TASEPs, these are the two independently located shocks. Okay. One thing that is a little surprising with respect to dimension 1 is that we found that if both drifts are positive, but if we are not in this case where both lanes are totally asymmetric, if both drifts are positive, you do not have blocking measures. You only have partial blocking measures, but you cannot have blocking measures in this case. So this is a phenomenon which we were a bit surprised at. Okay. And so the case that we could not completely solve when Q is equal to 0 is when gamma 0 is equal to gamma 1, because in this case we cannot quite discard the case that there could be a shock of amplitude 1. So okay. I still have the cases where you can have also opposite, still in the case Q equals 0. If you have opposite drifts on each lane, then you have a similar picture with partial blocking measures, but the partial blocking measures on each lane are going to be oriented in different directions, and there will be no global blocking measure. And if one of the lane has a drift and the other lane is symmetric, in this case, you can have just a partial blocking measure on the lane which has a drift, and just something that is full or empty on the symmetric lane. Okay, so I think this is the picture. So just I wanted to say a few. So I had a few slides on the cyclic ladder. So what just the message about the cyclic ladder is that these results partially carry over, but with less precision. We can give a general structured theorem where there are the measures which are invariant in the infinite directions, and there are possibly a finite number of shocks of different amplitudes ranging from 1 to n. But we can answer the question of Bramson and Liggett, and we can prove that any invariant measure is rotationally invariant. Okay. And so maybe to conclude the remaining time, if I don't want to be too long. So what are the main questions which are left open? First, we are a bit embarrassed with the set P1, because the set P1 is something that would carry shocks of amplitude 1. So these are not profile or blocking measures. And we exhibited such things when Q equals 0, but we do not know if these things exist when Q is different from 0. What we know is that if they exist, there is at most 1. The heuristics would say that such things are not expected to exist, because if you think of ASEP, you cannot have invariant shocks other than blocking measures, and this is connected to the fact that except 0, 1 shocks, all other shocks would fluctuate. So if you want to have invariant shocks, you do not have them seen from a fixed position, but we cannot currently prove this. Is there so this is, I think, the main open question. And if you look at the paper of Bramson and Liggett, this is in fact connected to their question 2, which is every invariant a V profile measure? And whereas they are positive about BL1 that we answer, about BL1 they say we think not, but we are less sure about it. So we think that there are no such measures, but this seems to be a more difficult problem to address, and probably other techniques are involved to answer these questions. So maybe I will stop. I had other things to say, but I don't want to go too far, so I will stop my talk here. And if you have any questions, I would be glad to answer them.
Thank you very much, Christophe. Are there any questions or comments?
I have a question. Okay, it's okay about exclusion in one dimension. If you're not considering translation invariant model, but only a model where your kernel, okay, say it's still nearest neighbor, but
yes,
it depends on the site and it's only ergodic. Okay, or just take random walk in a random environment. So in that case, I guess the blocking measures are it's just the same. You can compute them, but is there any way to find other types of measures? So like measures that would have a fixed density.
So do you mean blocking measures or reversible measures? Because I mean, is your question about a finite lattice or an infinite lattice?
Oh, you're on Z?
Yes, on Z, yes.
On Z, and you have your P depends on X.
Mm-hmm.
P and Q depends on X.
Yes, yes.
Okay, and say that you're always shifting to the right.
Mm-hmm. Mm-hmm.
Has anybody been looking at this the kind of invariant measure for this kind of?
Mm-hmm. Yeah, I'm not aware of references, but I guess certainly there are kernels for which you can do the computations explicitly, because for the kernels, for the computations to be explicit, you don't need a P of XY to be translation invariant. So
yeah, okay, but here your kernel would be random.
Yes,
kernel would be different at each side. So
mm-hmm. So you are talking about interacting particle systems in random environment. That's right. So, I mean, clearly, one thing that is maybe not very interesting, but if you have a random ASEP, then you will have blocking measures. No?
Yeah. The question is more like the non-blocking ones, the one that where you have.
You mean the measures which would play the role of the
IIT Bernoulli's.
Yes, I see. So there has been, well, what I can tell you is that with we have worked a bit on this question with Hélène Saada, with Krishnamurti Ravi Shankar, Tom Mountford, and Hervé Guilleul, and in particular for the a few years ago, we studied the hydrodynamic limit for the asymmetric exclusion process in a random environment, and then the invariant measures which are relevant for hydrodynamic limit problems are precisely not the blocking ones, but the ones you mentioned. So if you worked with a quenched random environment, of course, you will lose the notion of translation invariance. But we could show some results on the existence of a family of invariant measures. And one idea is that if instead of considering just the particle system for quenched disorder, you consider the joint disorder particle system, then you can recover some translation invariance. And then the usual techniques become partially accessible. So in this case, you can show the existence of a family of measures, but for these measures, I mean, in this talk, maybe the focus was more on the blocking side, but for the say translation invariant measures, it's a big question to know if for models not even in random environments, but translation invariant models with a conserved particle number, if you have a picture like for every density in a given interval, you have an external measure. This is an open question in general. So we studied parts of these questions for some model a few years ago, but this is in general an open question. For instance, if you take the exclusion process in an ergodic random environment, would it be true that for every row between 0 and 1 there exists an external measure that would have say mean or asymptotic density row? This is an open question.
Thanks a lot.
Yeah. You're welcome.
Are there any more questions? Christophe, have you also tried to see if the duality technique was working in this asymmetric context, or it was?
No, I have to confess that we haven't looked at the duality technique, so maybe this would be a question to ask to André, for instance, since he seems to have considered this problem in the symmetric case, but we have really focused on coupling techniques.
Okay, thanks. Let's see. So if there are no more questions, let's thank Christophe again. Thank you very much, and we update next Wednesday.
So thank you again for the invitation and for listening.
Thank you.
Bye.
Bye. Bye-bye.
Bye.